In this video, we're going to discuss section 3.2, general solutions of linear equations. This section is very similar to section 3.1, where we talked about second order linear equations. We are now just generalizing and expanding it to any nth order linear equation, but you're going to see a lot of the same definitions and results as the previous section. So to get started, let's talk about a nth order linear differential equation. So what that means is that your highest degree of your derivative is n, as noted here, circled in blue. And each of these y values are linear. In other words, the nth derivative, the n minus first derivative, down to the first derivative and the original y of x term are all linear to the first power. The polynomials in x need not be linear, only the y terms. So we have a remark here that unless otherwise specified, we're going to assume that all of those p of x polynomials and the function f of x are continuous. And we're also going to assume that p sub 0 is non-zero, which is a reasonable assumption because if it's 0, then it's not an nth order linear equation. It's an n minus first. So assuming that it's non-zero, we're going to divide each term through by p sub 0. And we'd just like to make this nth derivative be isolated and having a coefficient of 1, and then everything else is falling in line. So you'll notice that they just changed all of those polynomials from capital P to lowercase p, and same for f. We have the homogeneous linear equation that's associated with this equation, and I'm just going to note here this is non-homogeneous, and this is just by looking at this right-hand side, is the differential equation where that right-hand side is replaced with 0. So again, homogeneous means the right-hand side is 0. Non-homogeneous means you have a non-zero f of x function on the right. So then we have a theorem here, 3.2.1, says let y1 through yn be n solutions of the homogeneous linear equation on the interval I. If C1 through Cn are constants, then the linear combination of those solutions, C1y1 plus C2y2 out to Cn is also a solution of the above differential equation. So we saw this in the last section. This was called the Theorem of Superposition, which is a fancy way of saying that you can take individual solutions and then take linear combinations, and it is in turn a new solution. So a very important theorem that we're going to use over and over again this chapter. Theorem 3.2.2 states that suppose that the functions p1 through pn and f are continuous on the open interval, and then given numbers b0 out to bn minus 1, the nth order linear equation has a unique solution on the entire interval that satisfies the n initial conditions. So we're familiar with working with initial conditions. However, we've been working with first and second order differential equations. First order differential equations only have a single initial condition. Second order differential equations have two initial conditions. So when we go out to nth order differential equations, we end up with n different initial conditions. And so that's what this is noting. And it's also saying that this is a special case of the theorem way back in chapter 1 regarding existence and uniqueness. As long as we're working with linear differential equations, there is always existence and uniqueness guaranteed. All right, so our next definition is regarding linear dependence or linear independence, which we also saw in 3.1. So now we're going to look at n functions. We say that they are linearly dependent if there exists constant C1 through Cn, not all 0. So note that wording. It's okay if some of them are 0, but not all 0. Such that you can find a linear combination of these functions and they equal 0. And this is for all x. If the functions f1 through fn are linearly independent, if they are not linearly dependent. So again, thinking back to 3.1, it was really quick and easy to check for linear independence. We just took the ratio of the functions and we saw if they were scalar multiples. So it's quick and easy. This adding additional functions makes this quite a bit more difficult, because how are we going to check that all the different combinations of C1 through Cn in the world are not going to lead us to a linear combination equaling 0? It's near impossible. So the Wronskian becomes super important in this section. So again, here we're defining the Wronskian. It is the determinant of the matrix who is formed by writing the functions f1 through fn across the top row, and then all of the first, second, down to the n minus first derivatives are written in the rows beneath. And then again, we want to compute that determinant. So we'll review how we're going to work determinants in case you've forgotten that as well. All right, but the important thing is that these functions are across the first row, not the first column. And then derivatives, each subsequent derivative is a row below. So the Wronskian is useful because of theorem 3.2.3. We're going to use it as a tool to check for linear independence. And so again, this is same as in 3.2. I won't read through the whole thing, but the important thing to note here is that if they are linearly dependent, then the Wronskian is equal to 0. If they are linearly independent, then the Wronskian is non-zero everywhere. So those are the things that we're going to check here when we're working with sets of solutions and checking for linear independence. So let's take a look at our first example here, problem 8. Use the Wronskian to prove that these three functions, f, g, and h, are linearly independent on the real line. So they're telling you what the answer should be. You just want to confirm it with the Wronskian. So let's get started by writing out the Wronskian. I'm going to write the notation W of X, but we noted that sometimes people write W of F, G, H. So however you want to indicate that. And then the top row is a list of the functions. So e to the x, e to the 2x, and e to the 3x. So this is our first row. The second row is going to be the first derivative, e to the x, 2e to the 2x, and 3e to the 3x. And then finally, the third row is the second derivative, e to the x, 4e to the 2x, and 9e to the 3x. And from here, we would like to compute the determinant of this 3 by 3 matrix. So there are various ways to compute determinants. I am going to use what's known as cofactor expansion. And so I am going to choose to expand along the first row here. This is similar to how we computed determinants when working with the cross product in Calc 3. So again, here I'm going to expand along the first row. All right, and so let's see what we get here. Let's begin with that first entry, which is e to the x. I want to multiply by the determinant of the cofactor matrix. So let's see what the cofactor matrix looks like. I'm going to strike through the first row and the first column, okay, containing that entry e to the x. And if I strike through, whatever's left over becomes my cofactor matrix. So there's 2e to the 2x. Scoot this over. 3e to the 3x, 4e to the 2x, and 9e to the 3x. All right, so I've completed my first term in that first row. Let me erase those red lines. And now we're moving on to the next term in the first row, which is e to the 2x. Now, very important here, remember that as you're expanding along a row or column, your sign changes with each row. So this becomes a negative e to the 2x. And now I want to write down my cofactor matrix. So let's strike through that column and row and write out the terms that are left over. That's e to the x, 3e to the 3x, e to the x, and 9e to the 3x. Again, I'm going to erase my red markings and we'll move on to the final term here, which is e to the 3x. We switch signs yet again, so it becomes a positive e to the 3x. And then let's strike through to determine our cofactor matrix. All right, so we get that bottom left corner. So we have e to the x, 2e to the 2x, e to the x, and 4e to the 2x. All right, so we have our first approach here where we're knocking it down from a 3x3 to a 2x2. And then of course we know how to compute determinants of 2x2s. So I'm going to recopy my e to the x, and then I am going to use the cross multiply or multiplying across the diagonals. Remember our exponent rules here. X to the a times x to the b is x to the a plus b. I add those exponents. So this becomes 18e to the 5x. And now multiplying the other way and negating, minus 12e to the 5x. And now I'm moving on to the next term, minus e to the 2x. Multiply across the principal diagonal, 9e to the 4x. Subtract off the other diagonal, minus 3e to the 4x. And finally, we move on to our last matrix. We have plus e to the 3x across the first diagonal, 4e to the 3x, subtract off 2e to the 3x. All right, so let's simplify in each case. This is going to be a 6e to the 6x minus a 6e to the 6x plus a 2e to the 6x. And so, of course, my first two terms cancel, and I get 2e to the 6x. Now recall that the exponential function never vanishes. So I'm just going to mention that this is never equal to 0. And then if we zoom out here, according to theorem 3.2.3, if our Wronskian is non-zero everywhere for every x value, then we conclude that f, g, and h are linearly independent. So I'm just going to note that this is non-zero for all x values. And so theorem 3.2.3 implies that functions f, g, and h are linearly independent. And I'm just going to denote that by L period I period for linearly independent. And I'll just put a check mark because I know that was what I was supposed to show, and I just confirmed it. All right, bottom of page 2 has yet another theorem here. It says let y1 through yn be n linearly independent solutions. I want to emphasize we're assuming they're linearly independent. Solutions of the homogeneous equation as given. If capital Y is any solution whatsoever of the above equation, then there exist numbers C1, C2 out to Cn such that capital Y of X is a linear combination of those n linearly independent solutions for all X and I. This is a very, very powerful theorem. What it's saying in a nutshell is if we can identify n linearly independent solutions to the homogeneous equation, we have unlocked the mystery of every possible solution in the world. That any solution whatsoever can be written as a linear combination of these linearly independent solutions. So finding those n linearly independent solutions is really where we're going to focus our efforts in this chapter. All right, so this moves us to our second example, problem 16 from the text. A third order homogeneous linear equation and 3 linearly independent solutions are given. Find a particular solution satisfying the given initial conditions. So one thing I want to note here is that the book is stating that these are linearly independent solutions. You do not need to check that if they're stating it. Now, certainly if you wanted to check it, you could set up the Wronskian and show that it's non-zero. But again, if the book is stating that they're linearly independent, you can assume it. Find a particular solution satisfying the given initial conditions. All right, so we have this initial value problem. Those first two lines are the differential equation and the associated initial conditions. I want to take these three linearly independent solutions and I want to write out the particular solution. So I'm going to let that solution be represented by y of x. And I know that I can take the linear combination of each of these linearly independent solutions. So I'm writing that out currently. And my goal is to solve for C1, C2, and C3 so that it satisfies the initial conditions. Now notice that the initial conditions are based on y of x, y prime of x, and y double prime of x. So I'm going to go ahead and solve for the first and second derivatives, and then I'll impose all of those initial conditions at once. So let me write out the first derivative first. That's c1 e to the x plus 2c2 e to the 2x plus, I'm going to use the product rule here, e to the 2x plus 2x e to the 2x here. All right, and then finally, let's go ahead and compute the second derivative. That's c1 e to the x plus 4c2 e to the 2x plus c3 times 2e to the 2x plus 2, here again using the product rule, e to the 2x plus 2x e to the 2x. All right, so now let's impose those initial conditions. I'm going to change my color here to indicate that I'm doing a new step. I know that y of 0 equals 1. So I'm going to plug 0 into y of x. All of the exponentials become an e to the 0 or 1. So I get c1 plus c2 plus 0. All right, so notice that this x here makes that final term die. So what I have here is c1 plus c2 equals 1. All right, I can't solve for c1 or c2 because I don't have enough equations. So let's move on to the next initial condition. Y prime of 0 equals 4. And I'm going to plug that into the first derivative. So that gives me c1 plus 2c2 plus c3 times 1 plus 0. So in other words, I have c1 plus 2c2 plus c3 equals 4. All right, and then finally the second derivative at 0 is equal to 0. And that gives me c1 plus 4c2 plus c3 times 2 plus 2 times 1 plus 0. So if we simplify that here, we get c1 plus 4c2 plus 4c3 equals 0. All right, so what we have now is a system of 3 equations and 3 unknowns. We need to solve for C1, C2, and C3, and we have 3 equations to do so. So I'm just going to kind of label these as the y equation, the y prime equation, and the y double prime equation. So now we just need to solve this system. Let's change colors yet again. What I'm going to do is I'm going to solve for C1 as a function of C2. So that's 1 minus C2. And then what I'll do is I'll take this and I will plug it into, let's go ahead and plug it into y prime. So I have I'm going to write the y prime equation. This is 1 minus C2 plus 2C2 plus C3 equals 4. And let's simplify this where we can. This is going to become C2 plus C3 equals 3. All right, and then let's also plug C1 in the y double prime formula. So I have 1 minus C2 plus 4C2 plus 4C3 equals 0. Okay, so I have 3C2 plus 4C3 equals -1. So what I've done is I've reduced my system of 3 equations and 3 unknowns down to a system of 2 equations and 2 unknowns. So then you can solve this as you best like, whether you want to do substitution or elimination. I'll go ahead and substitute once more, and we're going to continue with our colors. I'm going to let C2 be 3 minus C3. And so if I plug that here into that y double prime equation, I have 3 times 3 minus C3 plus 4C3 equals -1. So 9 minus 3C3 plus 4C3 equals -1. So C3 equals -10. All right. And now I'm going to work my way up the chain to figure out what all of the other values are. So I'm going to take this value for C3 and plug it in for C2, which gives me 13. And then I'm going to plug 13 in up here. So I get 1 minus 13 is -12. I have now solved for C1, C2, and C3. So I can go back up to my original y of x function and plug those values in. So my final answer, we have quite the rainbow going on. Y of x equals C1, which is a -12, e to the x, plus C2, which is 13, e to the 2x, and then plus C3, which is a -10, x e to the 2x. All right, and this is my particular solution that satisfies the initial value problem. All right, so quite a bit of work there to do it by hand. If you have had a course in linear algebra and you're familiar with setting up coefficient matrices in your graphing calculator, what I ask you to do on quizzes and exams is to write down the matrix that you're using, and then you can just write like a little note like that you use row reduced echelon form or RREF in calc, and then you can state your answers. I am assuming that no one has had a formal course in linear algebra, so I will always solve them by hand, but you're welcome to utilize those tools within your graphing calculator. All right, so we want to talk a little bit more about the importance of the linearly independent solutions. We have a definition here. If we have the n linearly independent solutions of the homogeneous equation, here again, I want to emphasize the homogeneous equation, then a linear combination of the form C1y1 out through Cn is a general solution of the differential equation. When you see general, that means it's in terms of C1, C2 out to Cn. When you see the word particular, that means you want to solve for C1, C2, C3, which is what we did right here, right? So particular means solve for the coefficients. General means leave it in terms of those coefficients. All right, we have one more remark here at the bottom of page 3. And it's going to talk about a relationship between homogeneous and non-homogeneous linear equations. So let y sub p be a particular solution of the non-homogeneous equation. So I just want to color code those. Y sub p is the solution of the non-homogeneous equation. Recall that non-homogeneous means that you have that f of x function on the right. And also let y be any other solution of that same equation, so of the non-homogeneous equation. Then y sub c, which can be written as y minus the particular function, is a solution of the associated homogeneous equation. All right, so this yc is a solution of the homogeneous equation. We call y sub c a complementary function of the non-homogeneous equation. All right, so it's really important that you keep track of when we're talking about the non-homogeneous equation versus the associated homogeneous equation. If we take a look here at this equation, more commonly we see it written as the general solution to the non-homogeneous equation is the complementary function plus the particular function. So remember, this is the solution for the homogeneous dE. This is the solution for the non-homogeneous dE. And this is just any general solution for the non-homogeneous. So this is saying, look, if we can find a solution, a particular solution to the non-homogeneous equation, and we also know the complementary function, which is the linear combination of the linearly independent solutions of the associated homogeneous dE, then we can talk about the general solution for a non-homogeneous differential equation. This idea is going to become very important in a couple of sections. So we'll revisit this complementary plus particular solution here later on. All right, and then one more theorem here to finish off this section before we get to our last example. Theorem 3.2.5 says let yp be a particular solution of the, again, non-homogeneous differential equation on an open interval where the functions pi and f are continuous. Let y1 through yn be linearly independent solutions of the associated homogeneous equation. All right, and if y is any solution whatsoever of the non-homogeneous dE, then there exist numbers c1 through cn such that we take the linear combination of those linearly independent functions, which are our complementary function, and we add it to our particular function. So again, this is just saying what I stated earlier, y equals yc plus yp. Here again, this is unlocking the mystery of what a general solution of a non-homogeneous equation is going to look like. So keeping these last two theorems in mind, let's take a look at problem 24. It says a non-homogeneous dE, a complementary solution yc, and a particular solution yp are given. Here again, if they're telling you that they're solutions, you don't need to go through and check and verify. You are welcome to assume that what the book is saying is true. Find a solution satisfying the initial conditions. So we have our non-homogeneous equation, right? I just want to point out that this is non-homogeneous. We have a non-zero term here, f of x. And we have two initial conditions. And we want to find a solution satisfying those initial conditions. So what we know is y of x is the complementary function plus the particular function. So that is c1 e to the x cosine x plus c2 e to the x sine x plus 1. And all I want to do now is impose those two initial conditions. So I'm going to also find the first derivative since one of my initial conditions is related to the first derivative. And you know what, now that I'm looking up here, it looks like they're using a lowercase y rather than an upper. So let me go ahead and just stick with the book's notation, y of x here. All right, so the first derivative is going to be, I'll use the product rule here, e to the x cosine x minus e to the x sine x. Same here for C2, e to the x sine x plus e to the x cosine x. Derivative of x is 1, derivative of 1 is 0. All right, so now let's impose those initial conditions. We know that y of 0 is 4, but if we plug it into our equation, we get C1 plus 0, since sine of 0 is 0, plus 0 plus 1. All right, so conveniently, we're able to solve for C1 right away. C1 equals 3. And now let's use the second initial condition that y prime of 0 equals 8. And that gives us C1 times 1 minus 0 plus C2 times 0 plus 1 plus 1. So what we have here is 8 equals C1 plus C2 plus 1. And then I am going to plug C1 equals 3 into this equation. 8 equals 3 plus C2 plus 1. So C2 equals 4. And now we can plug these two values up into our original solution. So our final answer here is y of x equals 3 e to the x cosine x plus 4 e to the x sine x plus x plus 1. All right, and there is our solution satisfying the initial conditions. This concludes our notes over section 3.2. Thanks for tuning in.